What is up, you beautiful mofos? Man, I have got an absolute banger for you today. We will be doing the energy question, and I've made a massive worksheet. This worksheet took me ages to organize and write answers for. There will be a link for this in the description so you can download that and go through it. The energy question. Basically, by the end of this video, you'll be able to answer all the different types of energy questions they can possibly ever ask using one equation. It's called the work energy equation, and I'll show you how to use this equation. But from this equation, you can make all of these energy calculations, no matter what the scenario is or how many different forces are acting upon whatever. You have some theory that you need to know, which I'll quickly go through. So, what do you need to know? You need to know what work done is. Work done is work done by a force acting on an object. This is equal to the magnitude of the force multiplied by the distance moved in the direction of that force. So if the force has to be acting in the direction of the displacement. So if they're acting in the same direction, well, then the work will be positive. There'll be positive work done. If they're acting opposite, then the work will be negative. Okay, so that's the equation for work done. Force times displacement. Force and displacement are acting on the same direction. You also need to know the work energy equation, and this is the equation that we'll be using to solve all of these. 90% of these, basically. I'll do a question at the end where it's a little different, but you could still use this, but it's just easier not to. This equation, and all this equation is saying that the change in kinetic energy of a particle is equal to the net work done by a particle. So net work done on a particle equals the change in particle kinetic energy. It applies for all particles or objects. It's a very powerful equation. You'll see how powerful it is when we use it. Kinetic energy, this is the energy possessed by an object in motion. This equals to half mv squared. And see that obviously the change in kinetic energy will be the final. Initial minusing each other, and gravitational potential energy, that's just the energy possessed by an object in a gravitational, like due to its position in a gravitational field. So the higher it is, the more gravitational potential energy it will have. It's equal to mgh. And then finally, you just need to know the conservation of energy, which is basically energy just doesn't disappear. Energy stays constant in a closed system. So the energy at the start equals the energy. And so energy is transformed, but it's never just like destroyed. And that's it. That's all the content you need. This equation here it's really what we're going to be working with. And so these are all the questions. So it's a lot of questions here. They're organized in a specific way. So you start from 1 and work your way down. It's harder and harder actually as you go along, but you've got all of them there, and we'll be doing questions from all the kind of ways in this video, and I've answered them all for you. It's 60 pages long, so many written answers, and I answered them all in similar ways. I kept it consistent here because this one can be confusing. You might not know what to do. That's why we're going to be using one equation across the board. Okay, so you got that. So download that, please download it. It took me ages. Right, so let's jump into the questions. So I'll really explain the concepts here as we go through these questions. Okay, so a particle of mass so the mass of the particle is 0.6 kgs. The speed is, the initial speed is 4 meters per second. The plane incline, let's just draw this stuff out, and it moves since the 15. Okay, so it's moving down a slope like this. It's theta, mass of the particle here. So we'll have a weight Fg. It moves S down the slope. That's all they give us. So use an energy method to find the speed of the particle after it has moved 50 meters down the plane. Okay, so we use this equation, work energy equation. Change in K equals to sum of the dones on the object. Forces acting on the object, or the net work done. Okay, so our change in kinetic energy, this is just half m vf squared minus vi squared equals to well, okay, so what are the work done by the forces on the object? What forces are acting on this object? We have no resistance force, it's a smooth plane, and we have nothing else. The only force is this force due to gravity. And so we need the work done by the force acting in the same direction as our displacement. This is going to be the force due to gravity acting down the slope. The work done, because work done equals to S. And this is going to be positive, right? Because it's acting in the same direction as our displacement, or as the motion of our object. So it's going to be this, which is Fg sine theta. So our force down the slope times our distance move, or our displacement, is positive. I guess you could start off by saying, this is the work done by the gravitational force acting down the slope. This thing is going to equal to Fg F theta S. Okay, so we have this. Okay. And this Fg is just mg theta S this. And now we can rearrange for the final velocity, because that's what it wants. It wants the velocity after it's traveled 15 meters. So we can cancel the m's, times through by 2. We get fs squared, take that over. It's just rearranging. We get 2g sine theta divided by s plus vi squared. Square both sides. Okay, so therefore the final velocity of this thing, we plug all these values, and be 2 times 10 sine of what are degrees times s, which is 15, plus vi, which is okay. So therefore plug all this into your calculator. 2 times 10 times sine of 15 squared. Let me just now, so that was through using this equation, and it might have been a little overkill here to do all this, but when it gets more, if it gets more complicated, like in the next question, this equation is very useful. And just wanted to tell you, like, okay, another way you could think about this is, because a lot of the time they do it in the answers like this. Okay, well, the kinetic energy of this particle is increasing, right? It's speeding up, and it's having a loss in gravitational potential energy, which is going to kinetic energy. You can say that the change of energy, change in kinetic energy, is equaling the change in gravitational potential energy. Change in gravitational potential energy. That's another way to think about it. So if you find change in gravitational potential energy, well, what will that be? Well, that'll just be when the ball is here, it's going to have a change in height, right? This will be the change in height. So this, oh my God, it looks like this. So this is the change in height. This part here, this is s, and this is theta. Right, so the change in height is just going to be sine theta equals change in so by s, you get the change in height equals to s sine theta. Okay, so change in k equals to, this is mg change in h. This is mg times sine s. And this is the same as what we got here. Right? This is the change in kinetic energy equals mg sine times s. This is the change in kinetic energy equals mg sine s. This equation give the same thing if you think about it through the kinetic energy changing to gravitational potential. I mean, the gravitational potential energy changing to kinetic energy. This equation is just doing that for you, so you don't really have to even think about it. and which does make it easier when you're dealing with more complicated scenarios. This is quite a simple scenario. Okay, so I just wanted to show that. So basically what I'm saying is the work done by gravity, the work done by the force of gravity is change in gravitational potential energy. That's an interesting concept, and a concept maybe you should understand. Or you can just use the equation. That's kind of the understanding of where this, where this spoke of. The total mass of a cyclist and her bicycle is 75 kilograms. The cyclist ascends a straight hill. So we've got a scenario. And basically, with all of the scenarios where the object is moving in sort of straight lines, you use the work energy equation. Like in this question, you'll see why it's so useful. Okay, so a bicycle, so she's chilling here. Just say it's a box. This is theta. She has mass, so the hill's length is, let's call it S. S is 0.7, so we want it in meters. Theta is 1.5 degrees. Her speed at the bottom of the hill, so her initial speed is 10 meters per second. Final speed is 5 meters per second. There's a resistance to the motion. So we have a force, a resistance force, it's called Fr, to the motion. And this resistance force, the work done against this force is, so the work done of this force is 2000 joules. And the cyclist exerts a force of F in the direction of the motion. So she or he, okay, she's genderless, he's genderless, it's genderless. So she's just going to call her she. She's exerting a force up the slope. Okay, so this is our diagram. And now when you read that, you might be like, wow, that's a lot of information. How the hell am I supposed to solve anything for this or find it? Well, change in kinetic energy of an object is equal to the sum of all of the work. Okay? So therefore, the change in kinetic energy. Okay, so what forces do we have here? Well, we have this force, the work done by her, the force, we can call this the work done by F, and this is positive because this force is acting in the direction of the displacement. And then we have the force due to resistance, so the work done by the resistance force will be minus the work done by the resistance force, right? Because it's acting in the opposite direction displacement. And then minus, like before, the force due to gravity going down the slope, right? So this is going to be minus the work, so gravity, and it's minus because this time the weight or the force due to gravity is acting down the slope and we're moving up the slope, so they're acting in opposite direction, so it's minus. Okay, and now we know that the work done is for displacement, so we can just substitute these things in. Well, for this is F, it's S, F times S minus the work done of the resistance force we have here, so we can just keep it like that. And then we have this, which will be minus the work done down the slope by the force due to gravity. This is going to be 4Fg sine theta. Okay, and we have the change in kinetic energy here. Bf squared minus squared. Okay, so now we rearrange for this, and then we can find our answer. So take both of these over, we get Fs equals to half m of Vf squared minus Vi squared. Yep. Plus, this is mg. Theta. All right, we have all these values, so let's just plug it in. And F, this is S is 700. Half the mass times the final velocity is 5 and the initial velocity is 10. plus mass is 75. 10 sine of theta, which is 1.3 degrees. All of that times 700 plus 2000, right? Work done by against the resistance force, 2000. Okay, therefore you get 700 F equals 2. Well, just want to then plug all this stuff into. See, from that one equation, we found it. You didn't really even have to think about like what was going on. So 2, 5 plus stuff. 700 okay, I did all that and I got F, just calculated, divided through by 700 and I got 18. Okay, and again, I mean, if you want to think about it differently, well, this equation here, which we got from the work energy equation, we got the change in kinetic energy equals to work W R G. Remember from before what I explained, well, this is just the same as the change in gravitational potential energy. And so you could say here that the work done by this cyclist is equal to, if you take all these things, the change in kinetic energy, because we're getting a loss in kinetic energy, and then a gain in a gravitational potential energy, and then the work done by the resistance force, right? If you take all this over. So she is exerting a force onto this bike, and all of it is being transformed into a loss in kinetic energy, a gain in gravitational energy, and she's also doing work against this resistance force, which is pushing her down the slope as well. So that's another way you could think about it, and then you could have just worked that stuff out individually, but you got this equation without thinking about it from, yeah. Right, but you could have calculated all of these things individually and then thought about how the energy is transformed. And there's so many in the worksheet, there's so many like this with slopes and forces. And by using this equation, you're going to get all of these work done, and then you figure them out, and then you figure out different things from them. So just use that equation and everything will be fine. Okay, now for this one, I put this in. Usually they don't ask things like that, but I put this in because it's a bit different. Most of them are incline or just flat surfaces. But for this one, it's actually important that we use actually calculate the gravitational potential energy and kinetic. See when I do it. So a child of mass 35. Let's just reach this thing. So its mass is 35 kilograms. The length of the rope, we'll call it D, is 4 meters. Initially, P starts from rest. Angle here. Theta equals 45 degrees. And okay, given that there's no resistance force, so there's no force resisting his motion, find the speed of P when he's traveled halfway along the circular arc from his initial position to his position. So when he's halfway here. Or like he's halfway, yeah. Well, you have this gravitational force. So you could, if you wanted to, find the work done by the gravitational force in the direction of this of this displacement here, S. But then you'd have to find this, and this isn't exactly a right angle triangle, so that would be quite difficult. So I would recommend for these motion questions where they're arcing, doing something like that, just think about the energy transformations. So you have something here, it's being held up, it's losing gravitational potential energy, and all of that gravitational potential energy is being transformed into kinetic energy. So if we find the change in gravitational potential energy, that's the change in kinetic energy, and from that we can find the speed of it when it's at this point. So change in K equals the change in G. All of the gravitational potential energy is being transformed. Okay, so the change in G equal to mg change in H. What is the change in the height of this child? Well, it's going to be this height, this length here, whatever this is. Right, and we have this triangle, which is a right angle triangle. Then we have this triangle, so this is the change in height here. Call this length, let's call this length here, whatever this is, this height of the particle, that H2, call this like height here, H1. Oh, you see that at here, it's at this height, whatever. We don't know where the ground is, but it doesn't matter. Like, it's at this here, and the height, it's at this here when it's halfway through its motion. Right, so how do we find this? Well, this is just two right angle triangles here. So for this H1, we have, set adjacent, so B, so equals opposite, which is our H1, divided by R. So H1 for this first bit here is going to be, and for this lower, cos of, well, this one is going to be half of this angle because it's halfway through its motion. 2 is going to equal to H2. H2 equals E cos. Okay, so therefore our change in height here will be H2 minus H1. That's going to be D cos of theta over 2 minus D cos theta. Right, so therefore change in gravitational potential energy is mg times D cos theta over 2 minus D cos theta. Right, guess we can make it nicer. D theta. This equals to change in kinetic energy. Right, so change in kinetic energy equals to mgd cos theta over 2. Right, because all of the gravitational potential energy is transforming into kinetic. This is a half m Ef squared minus Vi squared cos theta over 2 minus cos theta. Okay, Vi squared is 0. Let's get rid of that. The m's will cancel. Vf squared is 2gd theta. I'm keeping it in general form. You can plug it in early if you want, but I just think it's better to keep it in general form. Then we can just plug everything in at the end. Therefore, the final velocity will be equal to 2 times 10 times 4 d cos of 45 over 2 will be okay. Cos 22 times 4 times 10, 2 square root of 4.4, so the final 4.16. second. So the reason I'm putting this one in, got another got B as well, but it's because, okay, here we're using, thinking about it, okay, that all the gravitational potential energy is changing into kinetic energy. So we find it's changing gravitational potential energy, we can changing. That's because in this scenario, it was actually hard to use that. Good, but it's hard to use the work energy equation. It is given that there's a resistance force to the work done against the resistance force as P travels from its initial position to its lowest position X. The resistance force P travels. Find the speed of P. Okay, hold up. Okay, so we got, let's just redraw. Here to lowest position. It's now got a resistance force. And the work done by the resistance force is X. X speed is 4. Okay, so see these things are the same. D is 4 meters. V initial is 0 meters per second. V final equals second. Find X. Well, okay, again, so let's just think about this. We have a gain in gravitational potential energy. No, we have a loss in gravitational potential energy. So what is like the gain in kinetic energy? That equal? It's just going to be half m v final v squared minus v initial squared, right? Change in, it's just going to be half of the mass. This was 35 kgs. 35 squared. This equals 2 squared times 5 is 280 joules. We're gaining 280 joules of kinetic energy. What's the loss in gravitational potential energy? It's just going to be mg change in h, change in gravitational potential energy. Loss in gravitational potential energy, well, what is the change in h? Similar thing before, this is the change in h. This whole length here is d. What is this length here? This length here, this is theta. This length here is going to be what? Cos of theta equals d over this length, so which one? So which one? Okay, so change in height equal to d, which is the entire thing, minus this h1, which is d cos theta. So d minus d cos this. Okay, so this equals to mg d of 1 minus cos. Okay, you plug all that stuff in, you get mass is 35 times 10 times 4 cos theta, which was, okay, this equals to 35 times 10, 4 times 400, 110 joules. Okay, so our loss gravitational potential energy is this, right? So now let's think about it. So that means that, you know, like the loss of our gravitational potential energy, this is going to equal to the gain in our kinetic energy, right? Because this is transforming into kinetic energy, but it's also being used up by the resistance force, the work done by the resistance force. So plus the work done by the resistance force. Work done by this resistance force here. Resistance. Right, so or you can write change in G equals the change in A plus the work done by the resistance force, right? That makes sense. You've got this gravitational energy and you're losing the change. That's what you're losing, and it's being transformed into the kinetic energy, and it's being used up by the resistance force acting on that object, right? So WR equals 2, or you can think of it like this. The difference between these two is going to be the work done by the resistance force, work against the resistance. Okay, so this is X, just going to be minus X equals 130. Okay, so joules. Okay, so I put that in deliberately because I wanted to show you, okay, you also make sure you need to understand like how energy is transforming and how you can calculate it without using that work energy equation. But for the majority of these questions, you just need to use this work energy equation. And I showed you how to understand that, you know, the work done by gravity is the change in gravitational potential energy. You should understand this equation, but basically if you use this equation for all of these questions, you're going to get the answer. This is just a fundamental law of work, and you will see on the worksheet that there's so many like this. Use this equation like all the time. Boom, boom. By using this equation, you can solve all of them. So I can say very consistent. Okay, so that's it. Download that. And now maybe I will do a brief discussion about energy because it's such a crazy phenomenon. All right, listen up. Energy is so vital for you as an individual. Basically, look, we were introduced to the idea of potential, energy and potential, and I just want to briefly just kind of hammer home into you that your energy is very important. And, you know, you have so much potential in you to do so much with your life. You're basically like a giant ass mass high up in the air, and you're just waiting to be dropped. You know, that thing like we saw here it has a massive potential energy, right? And you're able to transform that energy in positive ways. And there's many things that want to suck away your energy, drain you, put your attention and focus on the wrong things, doing mindless things which are not productive or doing any good for you or people that are around you. Your potential within you is huge. You have a massive amount of energy that is at your disposal, and the way you use your energy is the way you use your life. And so I just wanted to hammer that home. Energy, potential, you have it. You got it, mate. So use it. Don't let people take it away from you. Use it wisely. Okay? That's basically what I wanted to say. I'm not going to go into the metaphysics of energy here. I wanted to make this pretty practical. Okay? You have potential energy, so fucking use it. Don't waste it. Don't give it away to people that don't deserve it. Okay. Anyway, that's it. Like, subscribe, and I'll see you later.